Now I would like to speak about the dithering. So until now we had just some theory of placing dots, and it wasn't directly about dithering, although all these techniques can be used in the dithering of images. And the problem we have is a quantization error. So that means I have this kind of demonstration. There is some maybe analog input, which would be all the possible colors, which are real number, and then you want to make the colors digital. So this would be the individual bit values. So you can have all the different blue values, for example, and then you only have only here 4 values, 0, 1, 2, and 4 values of the blue color. And maybe you have only 2 values, maybe you have 4, 8, depends, but still you have some error in these regions, which is called the quantization error. And the problem with this quantization is that sometimes the error is not, random, and it kind of joins together, and you can have some artifacts in the images, which would be, for example, here, then there will be a better showing of this image. So the problem here is that these parts, for example, they are part of the same object, yet here you can see that they are completely distinctive. So this is a black part of the graph. So this is graph from above, and then this one is white. And then someone will say, okay, so these are completely unrelated parts of the image, but actually they are just a millimeter apart in the real life. The same is also in this image of the computer, where is the quantization even not just from grayscale to black and white, but from colored image to black and white, and then we lose a lot of information. I will go here to zoom on these two images, so you can see this part, and so for example, this part and this part here. This is one part of the inner circle, and here you can see that these are distinctive parts. And you can see that this is, for example, a moon-shaped object. So if you see this image, then maybe you think, okay, so there is some, these are kind of different slices of these different moon phases, and they are put into the image, and you completely lose the information, kind of what was the previous image. And also you can get this kind of zigzag artifacts here, which is here from the plotting of this image, and that you can kind of understand that it's just an error there in the plotting. Here it seems very important that these zigzag lines are there, and you wouldn't suspect that it's just this part which is plotted a bit darker. So you get, it's not just kind of losing the information in the previous image, but you kind of get new wrong information in the image, that you kind of think that there are these kind of different moons objects which actually do not exist here. And the dithering is, so I will go here or back to the slide. If we have these artifacts, maybe we can add some noise and we will lose the artifacts, maybe. And if we add the noise, then we will disrupt this error which is collected on one place, and we wouldn't have these blobs of one color, and we can make the error kind of more random, and then maybe it will look better for us. So this would be, for example, one line of pixels, and they have different values. This blue would be the original values. Here, just for the plotting, I plotted these red values a bit higher, so you can see how the dithering would work. And if we are just changing the colors from black and white, or deciding like if it's just below or above some threshold value, so if we threshold the values, then we would have all these blacks here, which this is the value of the pixel, so all these would have value 0, and then suddenly there would be this sharp step, and all of these would be white. And we completely lose the information about the gradient here. So if we do some dithering, and something like this, we will see some of the methods later. Then here I would have solid black, but in this part of the gradient, it kind of slowly changes, and here it's some of them are black, some of them are white. So here we know that it's more dark because there is more black than white. Then there is more white than black, and then there is just white color. So now we would have kind of steps of the gradient. So maybe something like that would help us to solve this problem. And now we lose the artifact of just creating the separate parts of the image, but we have some gradient somewhat shown. So this is one example of the dithering. So this is again from Wikipedia, image of David, and this one is in grayscale, and then this one is just the black and white thresholding. And firstly, we kind of lose all the information here in the hair, but then also these parts look completely different. It's a different maybe object, and this one is also maybe a different object. And maybe it's not even that this part would be the face, and this could be, I don't know, a cauliflower, and this is a face, and or a big brain or something. And then these parts, they kind of merge together, and maybe we would like to say that this part of the chin is something different than the background. And if we take this image and add some random noise, and then we do the thresholding, we have this image. And it doesn't help much, but we were able to break these blobs of color and break them into some different parts of the image, kind of. So now we don't see these parts as two distinct parts of the image, but we can see that it's some sort of transition between this part and this part. Although, to be honest, it doesn't look nice. It just solves the problem of breaking the big parts of the image into smaller parts of image. And you can see that if I zoom a bit, let's not zoom yet. So now we have this still ugly image, and we would like to see maybe something more in the image, and that's why we had this color theory before, and we know that we can use the two different colors to mix them in our eyes if we then maybe zoom out the image, and it will be small enough. And that's exactly what we are going to do. And I would like to show you a demo of this work with the pixels in this part of the video, and then I will show an algorithm how to do this dithering. In this part I will show a Macintosh SE, and there will be different colors shown with different pixels, and I will always try to blur the image so you can see how the colors blend together. So for example here, this is the boot. For the boot there are some pixels, and I will change the focus now, and you can see that the pixel values blend very nicely to uniform color. And I will show some other examples. So let's speed up a bit the booting part. maybe a bit speed up. Why was so slow back then? So I will show this changing of the wallpaper, and it will change the color on the left side. So the easy one is the black one, so it's just black screen. I think very interesting there. Now I have some dark screen, and you can see that now it's quite a dark gray, kind of. This will be a bit lighter gray. This will be even lighter gray. Now it was very nice. The blend of the colors. You can see that it's darker gray. This one is almost black, but not really. It's almost white. And this one is very, very bright, but you can see individual pixels, and that may be not good. This is, now it's also nice color uniform. And now it's again dark and black. One of the dithering method which we can use is order dithering, and that means that there is some rule which governs the dithering. In this case, I will show the Bayer matrix dithering, which is very common, and I think maybe you remember it from some older games, especially because of these crosses in the images. And we will do the thresholding not just if the value is greater than 128, but we will compare the pixels to different pixels in matrix, which is Bayer matrix called. And so, for example, if we go with the first pixel, we compare it to 0. If it's greater than 0, then we set it to 255, which is white, and if it's lower, then we set it to 0. So we go the first pixel, then we go to the second one, and we compare it to 64, and then the next pixel goes back to 0, 64, back to 0, 64, back to 0, 64. And then on the next line of the pixels, we do the comparison to 128, 32, 128, 32, and so on. And then on the next line, we go back to 0, 64, and then on the next slide, we go to 128 and 0, and we do this comparison to the different lines. And you can use a small Bayer matrix, 4x4, or you can use a bigger one. This one is 2x2, 4x4, or even 8x8. And this seems as a solution that it would work always, but there can be maybe some problem if you use a bigger matrix, for example, then maybe you have only one black pixel, or you have only one white pixel. So this could be this area, and here it blends kind of nicely the colors together, but here we have these individual pixels, and with the greater matrices we get worse and worse resolution. So this would be then a big problem for us if we want all the colors to blend nicely. So it depends on the scenario which you want or the method. Maybe it's a good method, maybe it is not. The very nice benefit of this method is that you can it's simple, and you can use all the different pixels. You can determine each value separately. So maybe if you do some use in accelerated GPUs, then you don't need to go through the whole image, but maybe you can do all these calculations parallel, and then you can get the value in few time steps. And also you can do some pre-calculations, because you know this 0 will be here and on the other, and then it will appear periodically. So you can take maybe some values at one time, and maybe I don't know, maybe you can do some pre-calculated tables or something like that. So there it is, and it looks much better than the random noise. There is also this void and cluster, which is another ordered dithering method, and then there is halftone one. This one is kind of similar to the one which is in print. So in print, this was done kind of physically by changing size in holes through which the light goes to for the exposition. So this one is a method on a computer which is trying to replicate that effect. And you can still see the halftone images in maybe a newspaper or something like that. And the problem which we have now is that these methods maybe have some artifacts on its own. So maybe here, these are the kind of lines, and you can see the line kind of in the image. And was there? Okay, so maybe there are some lines, but these lines, for example, here, there is no light present in this image, and then the image kind of doesn't really respect the texture, or it kind of creates a new texture there, which is not here. And also some of these points are then maybe visible if you don't want them to be really. Or I guess, well, you wanted them to be visible, but they are quite a lot contrastive, and you can see the mesh there. So maybe you don't want that. So there are still some artifacts in the image. And for that, we will need another method. But I would like to also show you how the colors kind of blend better than the random noise. So this would be the random image, and these are the ordered dithering. And you can see that now when we use the methods of the color theory, that we can blend the colors in our eyes, or maybe now depends on your display, maybe you also don't see the individual pixels, and then it's the software which does the rendering of these images on your screen, then it also maybe approximates that. But hopefully you can see it with your eyes that these colors blend, and they blend here nicely. And now these lines are more dominant. Maybe you would like here this kind of sort of part, so it doesn't seem that ordered. Or here you can kind of see maybe this kind of square pattern in which these dots are then in the image. Or maybe that could be just aliasing on my display, I'm not sure. And for that, we will use diffusion error, which is a diffusion error method, which would be the Floyd-Steinberg dithering. And that's the reason why we do this whole presentation. I want to show you this very cool algorithm. And how it works is we have some error, which is the old pixel. So we do the quantization of some pixel. We get the new value, which is the 0 or 255, although we can do this quantization in different scales, so it can be maybe 8-bit color or something like that. But we do this quantization and we get the new value, and we get the error of this old value and the new value. And we will distribute this error to all the surrounding pixels. And for that, we will use the diffusion, this diffusion error equation. So we take the error, multiply it by some constant, and add it to all the x2, which is these in the surrounding area, and the k is in this matrix. So this one is the pixel for which we did the quantization, and the k for this surrounding pixels is 0, so we leave them as they are. And then to this one, which is on the right, we take it and take 7/16 of the error and add it to this one, and then to this one goes 3, 5, and 1. And then we move to the new pixel, or to another pixel, and then we do the quantization, and we again distribute the errors around. And here it's important that these are 0, so we only distribute the error to those pixels below and to the one which is next in the line. And in this way we can go through all the pixels only once, and we do not have to backtrack the error to the previous pixel, so we kind of do this distribution into low right direction. And this would be a gradient image from black and white, on which I use the Floyd-Steinberg dithering. And you can see here it's black, this black part, and now it's get whiter, and now it's pure white. And I would like to show another demo of this on a Macintosh computer. Now we will see a Floyd-Steinberg dithering algorithm on the Macintosh SE, and this part is what inspired me to this whole video and the programming. So there are these images hidden on the ROM chips of the machine. There are the authors of the computer, and you can see these kind of patterns which are typical for the Floyd-Steinberg dithering algorithm. And I will change again the focus of the camera, and you can see that then the colors blend together quite nicely, and you don't see many of the artifacts in the image as it was for the order dithering, although there are still some different artifacts. For example, here above the heads there are some lines, and you can see that the colors are blending very nicely in the images. And we can see now the comparison between the Floyd-Steinberg algorithm and the ordered dithering methods, as well as the random noise. So it's much better than the random noise, that's for sure. We also solved the problem that we wanted to kind of distribute this quantization error and break these big parts of the image into smaller parts. So we've solved 2 problems. And also we don't have these sort of artifacts like this line here, and it kind of seems maybe more uniform or evenly spaced, all of these errors, all of these pixels, and they don't form these patterns or maybe these crosses kind of there. And it also changes quite dynamically with the the spacing between the pixels. So here you can see that they are 1 and 1, and then white, 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 and then you have only some matrix in which you can do the decision how the color what color you should print there. Here in these parts you have the whole white part, and then suddenly you need a lot of these dots together, so you can have a lot of them at one place, and then it evenly so there is kind of gradient way of showing these colors. So maybe here it's better it's better shown that here you need a lot of dark part, and then this part should be maybe much more whiter. So you can do this gradient of spacing of the dots. Here you have only with some matrix window some range of how the colors should change, and I think this one is then much better. And the problem is you can do it as in this case. You can't pre-calculate the values, and you can't do the parallel computation. So this one takes maybe a bit more time. And also another problem, and I will show that at the end in a small video, that the error propagates through the whole image. So if something changes maybe here, then this whole area in this way, this whole area would change the pixels a bit. So maybe you want that, maybe you don't want that. And on the contrary, this part, if you change some values in this region, then only this region would change. So maybe in some applications this is a better option than this one. Maybe you can use both options in a game. So maybe for background, only this part, there would be the Floyd-Steinberg dithering, and for an object moving like a platform or something, maybe you can use the different dithering method, and maybe that would be better for you. So there is another demonstration, and I think here the dithering really shows how good it is. So you can see here in this part that it looks almost indistinguishable from this image. You can see that there are really the gradients of the color, and you can feel that it's kind of wobbly texture of some graph. And even better is Macintosh, which has quite a lot of pixels, so the dithering is on very small. The dithering, the dithered image has a lot of so the dithered image resolution is so fine that the colors blend almost perfectly here, and it's much better than this image, although it uses the same information and it has the same number of colors. So here it looks very nice, I think. Although maybe in some cases you want the image to show the individual pixels, and then you maybe want to show some of the effects, like the glimmer effect, which is now here not shown. So it's not that one of the approaches is better or something is better than something else. It's just the artistic choice in different scenarios. So this was the introduction, and hopefully you will stay here even for the programming part. So see you in the programming part in a few moments.